give up on MMIX. By giving up, I mean I was convincing myself that at some point I was going to start writing code in MMIX. So I acknowledge that I want, but I still want to see the algorithms in action. So I'm going to start today, or I'm going to try to start today. My computer one allows me to write them in Rust, which is the closest thing that I'm there to get to the metal.
Okay. Yeah. Well, you have enough samples in MMIX to follow,
so I'm going to keep watching the videos and the debug through, because I am interested.
Mm-hmm.
What I gave up is in gain intuition on my own to write the code myself. So that's what I'm not going to do.
Yeah.
I acknowledge the reality that's not happening.
Well, have a look at the C programs that I've written. I've tried to remain, pretty faithful to the algorithms and also kind of faithful to the MMIX implementations. And it's actually kind of interesting because Knut definitely makes a lot of choices that are very specific to assembly. So, if you were programming in a higher level language with a lot of data structures available, you would not even think about doing things a certain way. And we've seen that, right? Like the way he sets up linked lists, and we'll see that today as well. It's pretty interesting.
The fun thing is that there is one of the best tutorial I have read about Rust for learning Rust. Not one of the best one. The one that actually got me, oh yeah, this is what this is about, is one that the tutorial is called Too Many Linked Lists in Rust.
Too many linked lists, okay.
So it's a tutorial about implementing linked lists in Rust. Super helpful to learn Rust. And the fun thing is that the guy who wrote it keep insisting all the way, you should never implement linked lists, but they are great for learning memory layouts and whatnot. So here we go.
Okay.
And in fact, it helped me to understand all the lifetimes and all the crazy things that go in Rust. Yeah.
All right. So the agenda for today is just the remaining portion of 521, sorting by insertion. And I just easily missed that those pages after shell sort, and I've just gone on to the next section, and I realized that this was something that I had intended to cover. And so there's two algorithms, programs kind of related to each other, and then there's a little bit of analysis involved. And I've noticed that even earlier, there's references in the analysis to inversions, and it does come up quite a bit in the calculations and the expressions that Knut uses to explain the performance. So I thought that we should probably just read a little bit about that preliminary material. So it is a little dense, so I don't expect us to really get too deep into it or discuss it at length, but just so that we know where to find things when we're interested in following up on something. So we'll start with that, and then we should have time for exercises today as well, and afterwards I'll do the step-throughs for the two programs that we'll be looking at. Yeah, Michael says maybe two more in rest. Yeah, so we should have all the languages covered after a while.
Go anyone? I think I got my mic fixed.
Yeah. You're coming through loud and clear. Great.
Brilliant.
Okay, so we are in volume 3, sorting and searching, chapter 5, and we will begin with this early section 5.1, pages 11 through 17. And again, it's 7 minutes, but there's a lot of material there. So if you just read like the initial portion and then maybe skim through the last 3 or 4 pages, that should be good, and then we can discuss it. Okay, so how far did we get? Anyone wish to look at the proof of the inverse of a permutation and the inversions?
The checkerboard proof.
Yeah, yeah, the
yeah.
Square proof. Okay.
I had just gotten there, basically, a little bit beyond there.
Okay. Yeah, so I guess, Arthur, you had a comment on the independence of inversions compared to the permutations.
Yeah, that was a quote from page, I want to say 13, before we got to H, which Miguel noticed. This section has the definition of that H, which is the harmonic series. But yeah, around page 12, he's saying, how do we count the number of permutations of one to n? And to me, it's very obvious, like, you know, how many possible values could there be for the first element? There could be n of them. What about the second one? We already used one, so that's n minus one, and so and you get n factorial.
Yeah.
And he's saying, like, well, that's not the easiest way to do it, because you have to account for how all those a's are mutually distinct from each other. So wouldn't it make more sense to say that the number of permutations must be equal to the number of possible inversion tables, because there's a one-to-one mapping between them. And we could just count the number of possible inversion tables, which is n times n minus 1, and so on. And it's not at all obvious to me, like, you know, just looking at it, that these numbers should be independent of each other at all. I mean, they must be, not only because he says so, but because there is this bijection between inversion tables and permutations, and we know there are n factorial permutations. But if we've made one choice for B1, it's not 100% obvious to me that there must remain n minus 1 choices for B2. Anyway, that was all I had.
Okay. Anyone else? Okay, so just so we know where this is and we can reuse later, let's go on to the actual sorting section, which is page 95 and 96. So there's basically just two paragraphs there going over this alternative approach. And so we'll just quickly read it, 3 minutes, and discuss that. Okay, so what do you think the algorithm will be like? How will it be different from the sequential straight insertion sort?
So this list insertion sort is, I think, interesting or different in that its interface is different. This is not an in-place sorting algorithm, right? We don't end up with, if we have kj, which is our initial array of integers, and we're sorting them, what we end up with is this array L of indices into, indices sort of into the original sort, yeah. Indices into itself and also into the original list at the same time. And we can sort of follow these lengths in L to iterate over K in sorted order, but we don't actually end up with a sorted list. And we can't use L to permute K in place either. We would have to make some other, like K2, and then we could fill it in by iterating over L. But this is not like shell sort or bubble sort or insertion sort, and that does not sort the list in place by exchanging.
Anyone else?
It avoids the memory movement. It avoids moving, like if you have a list of 20 elements and you find that the element goes in the 5th position, and the other ones you had to move elements 5 through the end over by one so that you could make space for the 5 that you found that belongs in that position. For the element 5 that belongs in that position. So you avoid moving, for each step, you avoid moving maybe about half the list over by one to make room.
Or the whole list.
Well, for insertion sort, yeah, we were moving whole chunks. For shell sort, we were just swapping elements. But even then, if your elements were expensive to copy, this avoids moving anything.
Yeah, but even for shell sort, we were moving the elements multiple times.
Right. And here we're moving them 0 times. So,
right. Yeah.
Okay, I just wanted to get some initial thoughts churning, and now let's look at the algorithm itself.
Otra paleta.
Okay, who can summarize? And maybe explain table 8?
Table 8 is the first few iterations of the insertion.
Okay.
So you're starting from the right. On the first one, there's nothing to compare, so you're going to put that 0. And what those numbers are, what those numbers will end up being is the link to the next item in the list. So at the end of the first iteration, you only have one item in the list, and it will have the link to the next item of 0, which is a pseudo record, and it just signifies the end of the list.
Okay, so then what happens after the first? So I guess the first key is going to be 703 in the list.
703, right? Because Knuth always reads from right to left. He always reads from right to left. That's a big hint. So at the next one, you're looking at 765, and you find that 760. There's only one item in the list. You compare it, and you find that its place is 716, position 16. So now you are going to put the pointer. I mean, that's the insertion. You're going to move that 0 over to 50, over to the point that you found, and put. You're going to move that pointer. I mean, you're going to set 2 pointers. The pointer where the 15 goes is going to get the 0, and 0 is going to point to the element that you're inserting. So at every iteration of this loop, you're going to stick in. The next iteration of the loop is going to is going to add the number 14 somewhere, actually the 14 is going to go because I'm talking about the 4th row of this list would be a 14, 16, 0, 15. Is that right? 14? Yes, 14, 0, 16, 0, 15. Because and it just happens to go at the front of the list, so there's nothing to swap.
Okay, what would happen at the next iteration? If we were to fill in a fourth iteration, what would happen?
So the fourth iteration is going to go through the entire list and find that all of the things in the list are greater than, so it's going to, that LJ is going to be 13. And that's where the 14 goes.
Yeah, you're right, but how will it exactly happen?
I don't understand the question.
Yeah.
I just wanted you to somehow step through it a little bit, so
we start with LJ looking at 16.
Right now it'll be at 14. Sorry, L0 is 14 at the end of the table.
We start looking at element 16, the 70. Yeah, you're right. We're going through this in the list order.
The
right?
last.
Yeah, so we start at 14. 677 is greater than 612, so we go to the next element in the list, which is 16.
Right.
16, we look at column 16. We see a 703.
No, would we reach 703?
We don't go any further.
Okay, so at each step, right? At each step, we have a particular element number J that we're looking at.
Right.
And we are going to do two updates to our array of integers here, L. We're going to update L sub J with the index of the successor of element J, and we are going to change one of our existing numbers to J.
Right.
Zero, maybe something else, right? One of them becomes J, and then element J becomes something. And those are the only two links we need to change, right? We're setting basically the next pointer of the predecessor of this node, and we're setting the next pointer of this node.
Right.
And that's what it means to insert it to the list. But to find that place where we need to do the insertion, we have to traverse the whole list. So this is still
not the whole list. That's the mistake.
Point, yes.
We only have to traverse until we find an element that's greater. So on the fourth row, the very first item in the list is greater than. So,
right. So on average, we're traversing half the list, yes. We're traversing linearly.
We're traversing a sorted list linearly.
Right.
It's already sorted. So, I mean, it just depends on what sort of disorder we have in the array. So, yeah. So any other comments or questions?
Oh, so basically, wait, is this like just building what the inversion table from the page 12? Is that what's happening here with the else?
No, I don't think it's the inversion table.
I don't think so either. No.
No, it's not an inversion table.
It's a permutation of the integers, so it's definitely not an inversion table.
Well, in the sense, so okay, fair enough. Because the 15, so it says like 603 has 15 elements in front of it, basically. No, not true.
No, it doesn't say that at all. Right?
It doesn't say that at all. It just says that the 15 goes to the
it's an
16.
index. It's not a count. It's an index.
Right.
Sorry, yeah, I'm trying to understand. So basically, is that the 15 goes to the 16?
No, it's not. No, it's a linked list. So it's saying that the successor of element J is element L sub J.
Right.
So for any given element, let's look at the last line of the table and look at...
I got it. No, I got it. So when this in 15, it said the successor of this is the other one.
So if you look at element 14 in the last row of the table, there's a 16, right, in the 14 column. So that means the successor of element 14 is element 16. The successor of 7 is 703.
Right. So the successor of 765 is nothing. There is no successor.
Right. Not yet. Yeah. Or yes. Because yes, that's the end of the list at the moment.
Exactly. I got it. Okay. I think I get it.
So when we're done, like once we go through all of the complete algorithm, we'll end up with a permutation of the numbers 0 through 16 in L.
Mhm.
Well,
in what do you mean by in L exactly?
L will consist of a permutation of the numbers 0 through 16.
Except for the first element. It won't have 0 through 16. It'll have 16 numbers in there. The first element...
No, it has 17 numbers because there are 17 different J's at the top of table 8.
Right, because 0 has the first element.
Okay, I got you. I got you.
0 is the end of the list, so it is included in the indexes.
Well, technically, it's the beginning of the bunch.
I got you.
There are two different meanings for 0. Right?
Yeah.
L
Yeah.
of 0 is the head of the list, but
Exactly.
in the table, currently at element 15, indicates that 15 is the last element at the moment.
Yeah, it's serving dual purposes, but the fact that he's using a 0 means that he wants that extra record at index 0. So then, it's sort of the special placeholder that's not going to be used for data.
That's why he says that it acts as a link, a circular list, because in the actual circular list, there will be addresses in memory, but in this case, it's just indexes. It's like a circular list of without memory, without using the memory.
Okay, so let us look at the program now. This is also a relatively brief look because I will be stepping through it later, but we'll have to switch to the MMIX supplement, pages 78 and 79.
Porque no terminaste. ¿Llegas ahí? Casi llegas a ver.
Okay, so anything to clear up? Did the program match up with what your understanding was of the algorithm, or any surprises?
I haven't given up on MMIX quite so much as Miguel, but I admit I'm not really following the my eyes glaze over at the program.
Okay, yeah, that's fine. I think that the only interesting thing is, well, there's a couple of interesting things. One is that there's the array. Each array has these records with the key and the link field. And so it's just the link fields that are getting updated in the array. So the list is being built inside the array itself. And with the assembly, he is able to sort of play these tricks with offsets and relative addresses. That would be a little more complicated in a higher level language, where you have to deal with different types. Here, it's not a big deal, but in the next program, the multiple list insertion, when I tried to write that in C, I did face a couple of issues there. But yeah, I think that is really it. And then the two-pointer thing, the Q and the P, that's kind of interesting the way he manipulates those. But what about the little bit of analysis at the end? Any comments on that?
And there his, what is that? Is that an upsilon? Whatever that is, the V. The thing that's not a new.
Yeah,
represents number
right.
of operations, and U represents the number of memory loads and stores, I think.
Upsilon is, no, upsilon is the actual cycles, and mu, I think, stands for the MEMS, which is the memory accesses.
Right, yeah.
Is that what you said? Maybe.
Yeah, I said operations and memory loads and stores.
Okay, yeah. Yeah, so, yeah, go ahead.
At the top of page 79, he does make the point that this does not involve swapping records. So this will be faster if there is more data to a record than just the key part.
Yeah. Yeah, that is the main benefit, that there's no copying involved, there's no swapping. It's just updating two links every time you find the right place. Any other comments?
Interesting the comparison it makes with program S. About that they are roughly the same, but for each extra octabyte that you add to the actual record that you have to copy over, by using L, you are improving the running time by 33%. That's what I get from it.
Yeah.
Just by avoiding the extra. So like now you don't care about the size of your data. Well, you do care, but it's less important.
Yeah, I have a feeling that, in the real world, if you had to use insertion sort, then this would be generally much, much faster for real data.
But this is still quadratic, so if you're talking about real data, you wouldn't use this anyway.
You may want to use it as some special case, right, where you've gone down to some smaller subset where, But yeah, generally you wouldn't. That's true. Okay.
Like if you know your list will always have the 10 elements.
Right. So you could use something like a merge sort, which would have better big O performance on a linked list. But maybe when you got down to lists of only a certain size, then you might switch to this. If this actually had one of those micro benefits. Maybe it doesn't. Maybe when we get to merge sort, we'll see merge sort's constants are also better. I don't know.
Right. So this is exclusively compared to the previous program, right? So it's not like universally this is great because of this. It's rather than you can see how we are improving from the previous algorithm to this one.
Right, where the previous algorithm is also selection sort, right? These are two versions of selection sort doing basically the same thing.
Exactly, yeah.
The elements around.
So
and you mean
like
insertion sort?
This is a small change, right? It's cool to see the small change. You know.
Right. Yeah. So I think that's a great assessment. It is this slight improvement, but he is introducing the idea of using links. Of sort of using this parallel linked list to add some meta information to the data without actually working with the data. So this is sort of this parallel, secondary array or secondary list. So that idea is really great. And then the second idea is the trailing pointer piece that often comes up in algorithms related to lists. So I think that's another big reason to understand it somewhat well. Okay, so let's go on to the material afterwards back in TAOCP itself. And there's on page 97 and 98, there's some general discussion of some other enhancements that can come to mind or people have tried for insertion sort. We'll just quickly read this and discuss in about 3 minutes. Okay, any thoughts or comments on this piece?
Well, I put in chat the final quote of this part, which I think is interesting. It's a nice little aha moment. It's saying basically, so we're doing insertion sort. We've got a bunch of stuff that we've already sorted, and we're taking one thing at a time and inserting it in its proper place. And then we're going back for another and putting it in its proper place and going back for another and putting it in its proper place. Wouldn't it be convenient if, let's say, we had two things at the end that we were trying to insert? Let's first see which of them is smaller and then which of them is bigger. And then we can just do one pass through this and put the smaller one in place and then put the bigger one in place. And then we're shortening the number of moves. We don't have to move everything twice. We just move everything once. And then, well, let's say we had three elements. The like half the elements at the end that were already sorted. Then we could put them into place much quicker. Right? So maybe we should just sort half and sort the other half and then merge those two sorted arrays together. Or even split it into fourths and merge the sorted fourths and so on. And then you end up with merge sort. So yes, you do.
Anyone else? Did anyone notice the name for the tree insertion, the author of the paper on tree insertion using binary trees?
So is this the Berners-Lee that is the same Berners-Lee of the internet?
No, it's very unlikely, right? Because this is from 1958. But I have a
Maybe he was
feeling
very old when he did that.
I remember reading about Tim Berners-Lee that his parents were also
Tim Berners-Lee, right?
Yeah, so I'm not sure whether this is his mother or his father.
This is his father, Conway, apparently.
Okay.
Berners-Lee, father of Tim Berners-Lee.
Yeah, so that's
cool. Your father invents an algorithm and the son invents part of internet.
Yeah, and you end up inventing an entire ecosystem. Okay, so it's a little past 3. Let's take a break till about 3:13, and when we come back, we'll look at the multiple list insertion. Okay, so whenever you get a chance, we're on page 99, just that single page, and about 5 minutes, although I think it'll take you less time than that. Okay, could someone explain the idea towards the end of the page?
So what I get is, so there is no mention of how you do it, but essentially for each number, each element that you're trying to, so the whole point is to, instead of starting to insert new elements in the middle of the list, you are going to get an extra, use an extra space for the possible slots in which, like ranges of the keys that you keep finding. So somehow for each key, you will have a way to, you want to put in one of these slots, because you decided that the slots have certain distribution, and you can know which slot each key is supposed to go, and by that you're going to reduce the number of insertions of movement that you'll have to do. Because that's it. So that, yeah, so you're saving some extra insertions, extra for each key.
How does that sound? Miguel, did you see the difference, the specific difference between the previous algorithm, the basic list insertion, and this one that's being proposed at the end of the page? Like in terms of the algorithm, what would be different, or in terms of the program?
So you will need an extra step to find out into which sublist you will have to insert the new key. So once you know which list it is, then you do the regular insertion sort in that chunk of the space, right? Like for example, after in the figure, the table that we put in page 99 says after 4 items, you have two of the 4 possible lists given the ranges of the keys. You have 2 elements in the first list and 3 elements in the third list. That means the next time a new element comes, your program needs to know in which list it's supposed to be inserted, and then go to that list and sort it there. So do the regular insertion for that smaller list. So meaning that you won't touch the list 3 or the list 1 or whatever it's supposed to be. So you're only touching the smaller chunk of the list that you need to look at.
Yeah, I think that's great. So the 2 main differences are, first of all, you need some way to map the keys to some specific list. You have these multiple lists, and then you also need a little bit of extra space for these different lists, right? And and that's what we'll see, like how much extra space is he actually going to use in the program. So unless somebody else has comments, we can just move on to the supplement. That's on page 79 through 80. Okay, how did this go?
That's a tough one for me, the toughest so far for me.
Yeah, it's tricky in a couple of ways, but if someone could just explain what they got out of it, or maybe Miguel, you could try whatever you got.
No, I'm trying to find where is the place. I have tried to find where the places are. I mean, I kind of have a vague idea, but I don't feel like
so going back,
the words.
Yeah. So going back to the 2 points that you made earlier, like how it's different from the straight or the basic list insertion. So the first point is, how do you map a key to the bucket or the sublist? So
it seems to me that is in line 10, right?
That is,
I mean, 10, 11, and 12.
11 and 12.
Yeah.
10 is just getting the key.
Fair enough. Yeah. I mean, like, yeah, it starts. The algorithm starts there essentially.
Yeah. So once you have the key, then to map it to the particular sublist or the head, that's lines 11 and 12.
Exactly.
So is that?
So you just
clear?
Go there and do the insertion sort there, sort of.
Yeah. So then the second point is right. The second point that you made was that after that point it's just like the basic list insertion, and that's true. Once you have the head figured out, then from that point on it acts the same way. The head will start out with 0 in it, and then these indexes will get updated as the list grows for each sublist.
Right. Yeah, but we were just describing the algorithm that we already knew. So I was trying to what I got not lost, but it was trying to keep. It was hard to keep up with the jump back and forward of the actual code. So I was trying to play the code exactly in my head, but saving what in what register and what's moving to what, and that's the part that was really hard to describe. Still is.
Okay.
So looking forward to seeing in the
there's definitely 2 or 3 really tricky parts in this one. But anyone else?
I didn't really try to understand the code, but looking at it now, I'm a little bit struck by the fact that he reuses label 0.
Yeah, right.
The top of one loop and the bottom of the next one. So that the numbers here don't really have any mnemonic value as far as I can see. He's just sort of saying, well, nobody after label 4 cares about label 0 again, so I can just sort of go back and reuse 0.
Mm-hmm. He's done that before. Also, I seem to remember that being done in some earlier programs too. So that's, you remember that's the whole point of the locally scoped symbols, the local symbols, right? It'll just find the closest one and use that.
Right. Yeah, it's physically possible to do this. I was just very surprised that once I had figured out, line 2, for example, is immediately jumped to 1. And then I looked at the comment on line 3, which said clear heads, and I thought, wait a minute, why are we skipping over clearing heads? Don't we have to do that part?
Yeah.
And then I figured, it didn't take that long, but I figured out, oh, okay, jump to the bottom of the loop and then jump back to the top. We've seen that in other loops.
So exactly.
The bottom 0 is the top. That makes sense. We start at 0. And then you get a little bit further down, and on line 9, it's jump to 0. I thought 0 was the top. Why are we jumping to the bottom with 0 now? But no, he assigns no meaning to these numbers at all, as far as I can see.
Why use a label only once when you can use it many times?
So that was the realization I had reading this piece of code that has a lot of branching. That just to start reading it, I usually were to skim through it and then trying to find out what the jumps were. But actually, things it makes more sense to stop reading the next line, just jump to whatever it tells you to, and try to find the logic from where you were reading to where you jumped. Otherwise, other things are happening that makes no sense. Like because there is no like subroutines like in regular languages you have.
I think that's really good advice, actually, Miguel. That, I mean, I don't know if I follow that, but I like that idea that you would just continue on one path, just ignore the fall through, right? So if it's a branch, then just assume the branch will be taken.
Yeah,
Follow that till its logical
rest.
conclusion, understand that piece, and then maybe go back and try to understand the alternative. Whereas in a higher level language, it's a bit more clear because you have like an if else or something else. Yeah. Okay, so we just have a little bit left at the end of the section, which is this analysis. And again, there's quite a bit of stuff here. I just feel like there's a couple of interesting things in there, buried in there. So, you may get something out of it, but we'll spend about 5 minutes on this. This is everything after program M on page 100 till the end of the section. Okay, what are your thoughts?
Well, one of my thoughts I already put in the chat from last time, that at the top of page 102, he's basically saying we have achieved order n sorting if if we assume that the elements are evenly divided among the range. Right.
Right.
Then we can do it on average, but not max, not worst case, just average case.
Michael, you're muted if you're saying something. Yeah.
Or maybe a little bit stronger than that, if you can get a good function that takes a key and gives the right list, so that if you have 10 lists, then you need a function that will take your key and assign it to the proper list so that they're approximately equally distributed.
Right. Yeah.
You could, the hashing function that they're using in this case just divides your input into m equal buckets by. I didn't when I go through the mix, I don't understand how you get a multiply in there. It's a divide to me. Like you would take the maximum value and divide it by the number of buckets that you wanted to use. And if that number came out to be 7, then 1 through 7 would go in the first bucket, 8 through 14 would go in the next bucket, etc.
Well, he's assuming, I believe, he's assuming that the input range, that the range of the elements is a multiple or is a power of 2.
Is a power of 2.
To use a right shift to.
I get the right shift. I get the right shift. I don't get the multiply.
But he uses a right shift to squish it down. But he's not squishing it all the way down to 1 or to another power of 2. He's squishing it down to, let's say, 5. So what you have to do first is multiply by 5 and then squish it down, so that your result is no longer in the power of 2 range. Now it's in the range of 0 to 5.
Multiply.
Well, that's why
I'm not following. Okay.
So
I believe it, but I'm not following.
We have going from let's use the power of 10, right? So we have 1,000 elements, and we want, or we have a range of 1,000. We have a set of numbers going from 0 to 1,000, and now I want to get them in the range 0 to 7. So how do I do that? Right. Step 1 is multiply by 7. Step 2 is divide by 1,000. The divide by 1,000, that's the shift part you're looking at. The multiply by 7 is the multiply you're looking at.
Arthur, can you use the numbers that are actually used in the program that I'll demo? So he uses 2 to the 10, 1,024, and 4 buckets.
Okay, so we have a range of 1,024. We're trying to get it down to 4. How do we do that? Step 1 is multiply by 4. Step 2 is shift by 10 to remove that factor of 1024. All right, multiply. And
okay, got it. I understand now. Thank you.
Yeah, and you'll notice that the actual divide or the shift right is E minus 3, and that's because it's being scaled by an octabyte in order to use it as an offset.
Yep.
Yep.
That
Okay.
part I got the shift. I just didn't get the multiply.
Okay. So in the stepthru, and if you look at the program that I've posted, that's in GitHub, I actually use a divide, and I've shown how the divide ends up being a multiply, because I also kind of approached it that way. But what Arthur said is great as well. That's a more direct way of explaining it. Okay, any comments on the math involved or the formula, the time computation? If not, we can just look at a few exercises. And if somebody has some preferences in terms of the exercises, please let us know. If not, we can look at a very simple one, or I mean, relatively simple, which is number 35, which says, how would you modify program M so that you do end up with that full sorted order?
Well, that's one where I think the point of the exercise is to write the code, which I am not motivated to actually do.
Yeah, we don't need to write the code, but you could just explain how it
you're
would
just
work.
splicing lists together, right? So you have basically two lists, of which one of them is the first bunch of elements and the other is the next bunch of elements, and you just need to find the end of this list and splice it onto the beginning of this list. So step through this one until you find the 0 that marks the end, and then set it to the head of this list.
Yep.
And patch together all the lists in that way. And so that's an order n operation, because you have to go linearly through the list to find where the end is. In fact, it would definitely be faster. You could do it in half the time, given that Knuth is not actually using linked lists here. He's using arrays of indices. And so if we're looking for the end of the list, we don't actually want to step through the list. We want to step through the array, because we'll find the end of the list in half the time that way. Just iterate linearly through the array until you find the 0, right? And then you're at the end of one list. And so you can cut your running time in half by going that way.
Linearly through the array.
Right, because what we've got here is a linked list, and ordinarily to find the end of a linked list, you have to traverse through the entire list until you get to the end, right?
Yeah.
But here, we've got additional structure. We don't actually have only the links. We also have an essentially unsorted list of all of the elements of the list. And if we go through in unsorted order, odds are we're going to find the end of the list in half the time.
But how? No, I'm not sure I follow how you would get the complete sorted order without actually traversing the list.
Well, we've already done the sort, right? Now we're just looking for the end of the list.
But the sort is in the list. The array is still the array. It's still the original array.
But we have to array L, correct?
I think that's what he's saying. You have to scan each list for the end of the list so that you can concatenate it to the next list, right? Don't you have to scan to find that 0?
Oh, because our lists are all mixed together, aren't they? Yes.
Yeah. But
yep.
here's an idea. Here's an idea. Maybe it's only partial, but what if you, instead of setting the head of the list to 0, set the first list 0, set that marker to be -1, and then go and set the second list to have a -2, etc.
My way actually does still work, even when the lists are mixed together.
Okay.
Because you go until you go through linearly through L until you find A0. This is the A list, but you don't know which one. So now what you do is you look at the element value and you say, which list is this element in? And now you know which list it is. And so now you say, okay, that's the end of list whatever. And you patch that up with the end of list whatever plus 1. And then you keep going until you find the next 0. You say, which list is this the end of? And so on.
But that's a sequential scan again.
Yes,
you end up going through the entire...
as long as the sequential scan you would otherwise be doing.
But you're doing it n times. You're going to have to do it. Oh, you're going to do the whole thing only once.
Right.
But you're
I'm going to go until I've seen n zeros, not until I've seen all n elements. Right.
You have to go through the entire list and look for all the zeros, or you could stop when you found all of the zeros, but that would be almost all of the list, probably.
Depends how many buckets you have, right? If I've only got 2 buckets, then it's only 3.
Then you go until you find 2 zeros, which will probably be at least
3/4.
At least 2/3 of the list.
Yeah. Exactly. And that's better than the whole list, right? If you always
start the
list in order, then the end of the list is always in the last place you look. This way, it's not always in the last place you look, and so the performance is better. It's also clever.
Okay, this one is on inversions, number 26. Can a file of n elements have more than n inversions if it is 3, 5, and 7 ordered?
Can you remind me what was 3 order or 5 order or 7 order?
So every third element is ordered if it's 3 ordered.
Oh, I see, like I see.
And then every
so
fifth,
like chunks of 3 are ordered.
not chunks of 3, but steps. No? Steps of 3.
Oh, every third. I see.
Yeah. Remember in shell sort, we the idea was that instead of an increment of 1, you would use an increment of some h, and then you would vary the h.
I forgot that. Yeah.
Down to 1.
Yeah, if you look at 1, 4, 7, 10, they're in order. And if you look at 2 plus 3 is 5, 2, 5, 8, and 11, they're also in order. But 1 and 2, you don't know which one. It could be either way.
Got it.
Reorder. If you take the list and go every third element, there's 3 possible lists that you'll come up with. There's 3 sublists that way, and they're all in order. Which problem number is this?
This is number 26.
So I'm a little confused too about if he's saying that a list is ordered by is 3, 5, and 7 ordered, or is like for each of those cases.
For each of those steps. So I don't know if you noticed, but this is an M35. So it is.
Yeah, I did notice.
It is expected to be a little challenging.
That's
but
what
if anyone has ideas, that would be great.
Yeah, that's what I want to make it very, very clear.
Looked interesting.
Because the inversions are on the whole list, not on the 3 part or the 5 part.
Yeah, so it's saying, could it have more than n inversions?
I mean, if it's somewhat ordered, intuitively I would say that you should have less naively, you know, inversions. So is n the max number of inversions that you can have for sorting any regular list?
Bueno, pero él últimamente no, y lo ha mejorado bastante. Y le dedica tiempo a hacer cantidad, porque hoy está ahora está ahí.
No, I think we discussed that the number of inversions is n
It's
factorial.
n factorial, right?
N factorial. So let's say that
Yeah.
we're looking at, since it's 357, we should pick something that's at least 7 elements long. I don't know what is 7 factorial? 720? Oh, that's maybe 6 factorial. But anyway, it's a big number, right? It's a pretty big number.
So if it's 3, 5, and 7 ordered, then any pair of elements that differs by a multiple of 3 or 5 or 7 is going to be in order. But you have plenty of pairs of elements that don't need to be in order that way. So I think the way I would approach this is sort of make a, what's a good word, like a sort of a netting, I guess, of for a given element, which other elements are related to it by 3s, 5s, 7s, or some combination thereof, and which elements are sort of
some kind of graph? Do you mean some kind of graph, Arthur?
No, I mean you have an element, and then 3 elements before it is related to it. 3 elements after it is related to it. 5 elements before is related to it. 6 elements before is also related to it because you can get there with a 3 and a 3. 8 elements because that's 3 plus 5. 10 because that's 3 plus 7. 15, and so on. 12. But there are certain numbers that you can't express as 3s plus 5s plus 7s, such as 11. So a number and the number 11 before it are not related. And so that might be an inversion. And for that matter, the number and the number 2 less than it, or 1 less than it, might be inversions. And so I'd sort of build up these nets somehow. And again, this is just if I were trying to construct it by hand. This is not in any way a good mathematical structure. And then just fill in the gaps. You have one that's a net of things that are related, and then you have the gaps, and you fill in the gaps 1, 2, 3, 4, 5, 6, 7 until they're all filled, and then you go back and fill in the rest 8, 9, 10, 11, 12, and that will tend to maximize, interleaving these sorted sequences, where the sorted sequences are just consecutive numbers. Right? It is going to maximize your inversions, I would think.
Well, what's striking is that this number is very small, right? I mean, what he's asking for is a very small number compared to the number of inversions that you could have. And so that seems like a really striking upper bound, whether it's true or not.
So would it make sense to try to see, we know how many numbers will be in the right place. So those numbers won't need to be inverted. They will be there, right? So there is like minus some inversions due to the fact that every third number is already ordered. So how can we does it make sense to try to count? If relative to n, how many less inversions we will have based on that?
I'm not sure I follow, like how many fewer inversions you would have compared to n, or?
So this is sort of the related to the binomial. I forgot the word. Index, no. Binomial term, I don't forget the name of the thing. Like when you do have of n elements, you will have to make permutations for 3 of those. Like it's n factorial divided by n
divided by n minus 3 factorial.
Yeah, exactly. And that's the number of permutations that will have to happen for the rest of the numbers, right? That's the rest of the Is it?
I'm not following this at all. But by the way, I looked at the answer, and the answer is yes.
Oh.
Very helpful.
Okay, so that's not a good answer. That means it's not as like you'd have to show that you can actually have more than n.
He gives an instruction of like, you can do it this way, but not anything that I understand as
okay.
The proof.
Okay, any other insights anybody want to discuss?
No. I was trying to talk about the binomial coefficient, which is the whole thing that how can you how many permutations can you have of subsets of one bigger number? I was trying to see if that takes us anywhere. Does it?
I don't know, but worth looking at the answer, I think.
It sounds, I mean, he just used it for the previous, like, to make the analysis of M. So that makes me think that that has to be related, right? It makes sense because you're talking about chunks of stuff. So if you're talking about chunks of a big list of n numbers, it makes sense to start thinking about the whole point of the of chunks of permutations there, right? So you will have to make permutations every 3 elements, presumably. Anyway, all right, let's give up.
Okay, so the next meeting next Saturday is the basic sorting technique will be bubble sort, and then we'll look at a better version or something that uses similar ideas to bubble sort, and Knuth calls it merge exchange sort. But it's essentially a method that was discovered by Batcher, I think Ken Batcher, I forget his first name. But it's also known as odd-even sort, and I found a couple of other names that people use for it. I just called it Batcher sort in the title. And but it is pretty interesting because it'll introduce this idea of being able to parallelize a certain step, and there's other more advanced sorting algorithms that are based on the same idea as well. And if you can do that, then it's supposed to be one of the fastest sorting algorithms around. So with that, I will switch to the debugger.
Very back.
In my internet browsing last week, I came across another interesting simple sort algorithm. It was implemented in Python. It was called sleep sort. And the way that it works, the story that it works is the Titanic is sinking, and the conductors on the ship has told everybody on the ship has to count up until their age, and then they can get on a lifeboat. So the idea of sleep sort, it's kind of like a radix sort. You start a thread for every element that you're going to insert, and you wait that number of seconds, whatever that element is, and then you insert it. And so you use threads, and so the first threads that finish are the ones with the lowest keys.
Yeah,
not something that anybody would ever use, but it was just when I saw that, I thought, oh my God, that belongs in Knuth. How many M's and P's and Q's is that one?
Well, that's an interesting one because either it's quadratic, because now you've got n different threads running, and you're context switching between them, so you end up with n squared. Or you're using the OS to do the sleep, which is more likely these days, and then you're basically just farming out the sorting to the operating system. You're giving the operating system this set of wake-up times and saying, sort these for me. And then you can speed the clock all the way ahead and say to the OS, okay, now it's this time, wake me up in order. And you've just pushed the sorting of the actual threads into the kernel.
So now I've got rock sort and sleep sort to my name.
Yeah. I was also looking the last couple of days for visualizations of sorting because I thought that would be an interesting thing to maybe go over once we've covered enough of these techniques. So I found some really good ones, especially the ones that use both sound and some visual movement. Those are pretty good. So
yeah, but it doesn't belong in Nuth unless you can implement it in MMIX. Yeah. We'll see. Okay, so this is first program L, which is the basic list insertion. And the idea, I've summarized the idea on lines 8 through 11. By the way, is the size fine? It's readable, everything is clear?
By the way, it being after 4, I think I'm going to drop off.
Okay, thanks a lot, Arthur. See you. How does it look, Michael? Is it pretty clear? Okay, cool. So the idea is that instead of having to move the keys or the values inside the array, as we did in straight insertion sort, what we're going to do is we're going to add another field to each record, which is the link field, and then we'll create this sorted link list within the array of records. So the extra space is now for this single link field per record or per node, but it's still just one array that is being sorted. And so you could think of it as sorting in place, except that the records themselves are not going to move. So we already saw the algorithm, and so now what we'll do is just step through the program. And the way it works is that, let me show you the main program, which is down here. So the sort subroutine takes 3 parameters. The first one is the address of the array that needs to be sorted. And the second one is the size of the array, the number of elements to sort. Sorry, it's just two, not 3. And then the subroutine is called. Let's look at the data that we're using. So that's over here. And you can see that each record is a pair of octas. So the first octa is the link field, and the second octa is the actual key. And over here, this is the first record. Okay, the first node, the first octa is 0 because the links are not set initially, but the key is 5, and then the next record is 03, then the third record is 02, and so on till the last one. So the actual keys are 5 and 3, then 2, then 5 and 7, and this is what we're sorting. The special head record or head node is the first one, and that's just a pair of octas that are both 0, starting out at least. There are 10 keys in here, so the size is 10. This is what we would expect to have at the end, or be able to get at the end when the thing is sorted. And this is again just for visual verification. It won't actually be used in the program. So we start out at main, and I've already got a breakpoint set at the start of the sort subroutine, so we can just go from there. So which is up here. Okay, so this is the start of the sort subroutine. And let me just tell you something about the registers that are being used. So this lowercase link, which is register 0, that's going to be the base address of the data array. So this will stay fixed. And then n, which is the second parameter, this is register 1. This is the key register, register 2, which is being used as a base address for the key fields. And so this is again a pattern that you'll see in MMIX a lot, at least the way that Knut and Martin Ruckert have written the programs, which is that when you want to iterate over some records, you fix sort of the start of the array as the base address, and then you just use an offset to add to that base address every time you need it. So this key will be the base address for the key fields. So what that means is that with this base address, we will be adding some multiple of this offset, because the key field is the second field or the second octa in each record. And so you know, the first record will be like 1 times 8, and then the second will be 2 times 8. And remember that the record at index 0 is special. It doesn't actually have data in it. Okay, so then when we start, we're going to start stepping through the sort function. The first thing that's going to happen is we set the key register to the base address that we want to use for accessing the key fields. And this is simply just adding the constant uppercase key to the address of the array that's been received in register 0. So that's done over here. So $2 becomes this address. I've got these as decimal because we'll be looking at keys for the most part, but this is the address that's going to be used for the key fields. So the base address, and then there'll be some offset that's added to it. The first thing that we want to do is to initialize the head node so that it is pointing to the last node, because we know that that is, you know, just one value. We don't need to figure out its position. We can just start with that. So we'll start out setting the link of the first head node to the last entry of the array. And then we're going to move down the array, and we're going to start updating this sorted list that we're building inside the array itself. So this J is going to act as an offset or as a counter for iterating through the array from the end. So what it's set initialized to is the number of elements multiplied by 2 to the 4. That's 16, because each node or each record is 2 octets. So that's done. We have 10 elements So J starts out at 160. And over here, what happened was that we stored what was in J, which was 160, to the 0 link location, meaning the link field of the first special record. So this is essentially initializing link to start out at the last node, and it's actually pointing past the last record, because what's going to happen, as we've seen in MMIX loops, is that there's some initialization before the loop that takes you directly to the branch at the end of the loop, so that when it starts out, it'll either have the appropriate decrement done to it or the increment done to it, and this is often the case. So in this case, we're actually at n+1 because we have that extra first node at the beginning. So this is not past the last node. This is actually the last node. And so we're initializing that last node to have a link of 0. So now after this point, if we now look at the data array, so you can see the data array down here in this first panel. This pair is the first node. So this value over here is the link field, and this is the 0 of the first node, which is going to remain unused. So this doesn't actually matter. But then afterwards, for this first record, we have 0 as the link field and 5 as the key, and then we have a 0 again for the link and 3 as the key. And so you can see all of the other nodes, and let me expand this a little bit. You can see that all of the other nodes have the keys and the link field set to 0. So I think that this actually, the array ends over here. This is the last node. So 099 is the second to last, and 05 is the very last one. Okay, so then we start the loop. And as I mentioned before, we are now going directly to the end of the loop, to the branch. We decrement J, and it starts the first iteration of the loop. This loop is a nested loop. So the outer loop is iterating over the array in reverse. So it starts from the last, or actually the second to last entry, and it works its way down to the beginning. These values are all unsorted right now. So the outer loop is over sequentially over the array of unsorted keys. The inner loop is going to be over the sorted list that we are generating inside the array. So the first thing we want to do is we want to retrieve the first sorted key. In other words, the first entry of the linked list. So for that, we know that the head node will point to the first entry of the first node in the sorted list. So we can get that index from link 0, or L0 as we call it in the algorithm, and that's going to be stored in P, or loaded into P, which is register 4. So let's see what that is. And that is 160, which we expect because that's how we initialized the sorted list. So 160 is the offset in bytes of the very last node and we need this pointer Q to trail P, because when we find the proper position of the unsorted key that we're trying to insert, or we're trying to put it into the sorted arrangement, we'll need to insert it before a key that we found that is greater. So at that point, we'll need to know what was preceding this particular node, and that's what we're calling Q over here. So Q is going to trail P. So initially, Q needs to be set to the head node, which is at index 0. So that's what happened here. So now we get the next unsorted key, and you can see that's 99. And so down here, you see this is the second to last node. So this is what happened. The first node in the sorted list was just selected to be the very last node of the array, because one node is always sorted. So that was a 5, but now we want to figure out what will happen to 99. So we know that 99 is bigger than 5, so we expect that when the comparison happens, we'll go past 5, and then we'll hit the end of the currently sorted list, and then we will just insert 99 at the end of the, not insert 99, but we'll update the sorted list to point to this node at the end. And so we do the comparison between the two keys, and in this case, the unsorted key that's being compared is 99, the sorted key is 5, and when we do the comparison, then 99 will turn out to be bigger than 5, and so the result is going to be +1. And in that case, we know that the unsorted key is now bigger, so we have to keep going, right? Because it's the sorted list is in increasing order, so we have to keep going. And that alternative is the fall through. And so when you keep going, you need to update the 2 pointers, the Q and the P. So the first thing we do is we set Q to P so that it's trailing P, and then we update P to be whatever its link was, right? And in this case, we're at the end of the list. We only had one node so far in the list. So P will become 0 at this point, which it did. In register 4, we see a 0 over here, which means we've reached the end of the list. If we've reached the end of the list, then that means that we should now insert or update the links to reflect this new unsorted key in the list. So that's what's going to happen. At this point, we are going to insert insert in quotation marks by updating the links, these 2 links. And so here's the key difference between this list insertion and the straight insertion, that there's no movement of the keys or the records themselves. It's only these links that are being updated inside the array itself. And so we update the link of the previous, the trailing Q, to be this particular node, which is J. And so down here in memory, you can see that the link for 5 is now saying 144. Why is it 144? Because that's the offset of 99, this key over here, which was one node before. Each node is 16 bytes, and this was at offset 160. That was the last node. So the node before is at offset 144. And then when that is done, we need to update the link of the node that we just inserted. Because it's the last node, we are going to set that to 0. It's already 0, so there won't be any change shown in the debugger. So that's what happened. So now we're done with inserting this one new unsorted key. In our sorted list, what do we have? Our sorted list starts at record 0. So if we start at record 0, we look at the link, we have 160. So 160 is the very last node over here. So we go here and we see that the key is 5. So that's our first sorted key, 5. The link for this node says 144, which we know is the node before. So we follow that and we end up at this node, which has key 99. So the sorted sequence so far is 5 and then 99. And then the link for 99 is 0. So that means this is the very last node in our sorted list so far. So the next iteration of the full loop needs to begin, because now we need to handle the next value in the unsorted array, which would be the third from last node, and that is this one here. So the key is 2. So what's going to happen with 2? We're going to start comparing it with 599, except that once we compare it to 5, we'll find out that 2 is smaller than 5, so then we don't need to go further. So at that point, we'll insert, again in quotation marks, we'll update the links to reflect the fact that 2 is the smallest key so far. And so we should see that happening. Just going to step through that. We start looking at the list. And at this point, what has happened is that 2 compared to 5 turned out to be smaller. Since it's smaller, we need to update the links. 5 was the very first node in the list. So updating the links this time means that we have to update the head node, because that's the start of the list. The head node needs to point to the new unsorted node whose position we found, and that is at offset 128, right? Because it's the third from last. The last one was 160, and each node is 16 bytes. So the head node now points to 128, and that is this entry over here, the 02. In the next instruction, we expect that the link for this node needs to point to the very last node. So this 0 should turn to 160. So that's what we expect. And that's what happened. So this is how the list is getting built up. We are just going down the array in reverse. Every single time we look at the new unsorted key, and then we look at the head of the sorted list, start traversing that sorted list until we find a value that is bigger than our new unsorted key, and at that point we found its position, or we end up at the end of the list and then we append it to the end of the list. So what I'm going to do here is set a breakpoint, I think over here, where it updates the links after the insertion point has been found, and then we should be able to step through this much faster. So what is going to happen next? We need to handle -3. -3 is the next unsorted value, and -3 we know will be the smallest key so far, because right now we have 2, 5, and 99. So -3 needs to be inserted at the as the very first node in the sorted list, which means that the head will need to change. Head will change, -3's link will change to point to the current first node, which is this one here. So that's what we should see. Okay, so that's what happened. Head became 112, which should be the offset of this record here, and -3's link turned to 128, which should be the offset of this node, which was the previous beginning of that list. So this will continue to happen. Let me continue again. The next value will be 11. So the offset or the link for 11 changed to 144, which was the offset of this guy, of 99. And the one before 99 was a 5 previously, so that needed to be updated to 96, which is the offset of the key whose value is 11. So we can just continue doing that. We've updated the link for 7, then updated the link for 5, updated the link for 2, and updated the link for 3. So now we have sorted all of the keys in the array except for this last one, which is a 5. And when we're done with this, then the entire array is sorted. So that was it. So that's the last one. So now, as you can see, there was no movement of the keys themselves. The entire array stayed exactly the way it is. All that happened was that these links that were paired with each of these keys got updated. So we now have the complete sorted sequence known to us, because if we start from the first head node, it says go to 112 as the smallest, for starting the sorted sequence. So at offset 112, that'll be the smallest key, which should be this one, -3. And then once you're at -3, its link says 48 is the next smallest one. So that would be this 2 over here, right? So 48 divided by 16 is 3. And so on, right? So now we know how to get the sorted sequence. So when we're done with that, going to return. There's no return value. And so that's it. So we're done with the sorting with the basic list insertion. Michael, did you have any questions? I don't know if Miguel is still there. If you're still there, if you have any questions.
Yeah, I'm here.
Oh, cool. Very nice. Any questions about the Stepthru or the MMIX?
As I said, I'm not going to try to reproduce the MMIX code in Rust. That makes no sense.
Okay.
I will try to execute, to implement the algorithm as is described. I will try to avoid, more helpful data structures that are available.
I think that's a great idea. And as I said, I've done this in C, and for the most part, it translates pretty easily. The only thing is you have to, like I had to, figure out how a for loop would be structured exactly, and still be faithful to his go-tos in some sense, right? So don't come up with your own sort of sequence. That was one tricky part. But the other one that's a little more challenging, and this would be true for anyone who wanted to translate Knuth's algorithms into some other higher level language, would be that in MMIX, he has so economical code. Like this is like so compact, and so, like he doesn't waste anything. So that is one thing that I really like about the MMIX, is that it gives you a lot of appreciation in terms of what can be done if you did have that control over these bits and bytes, and he makes the best possible use for it. And so when you're trying to translate that to some higher level language, that can be a little more tricky, especially in a typed language where, so for example, I can't just arbitrarily add bytes to anything, right? It's like there's a type. If it is an array of records, then, I would have to cast things, and it could get pretty ugly. So that's the other challenging part.
There is a lot of value in following the MMIX programs, because it's like, this is how you really, I have jokingly told my friends that these books from Knuth is like, how to rebuild computers after extinction level event. Human civilization is destroyed, all you have is Knuth books. You should be able to build computers again, right? In a way, like you have the algorithms, and this is how you actually have to use them. Like,
thank you, Michael.
With any magical, hand waving solutions.
Yeah. He does, and as you know, there are additional books and documentation on MMIX. So what he's explained in the fascicle one, and what we see in the MMIX supplement, that's really meant for programmers, sort of at a high level, at the application level, that you want to use MMIX for solving problems, for implementing algorithms. But if you really get down to the details, he has a whole other book on that called MMIXware, and there's so much detail there. Like if you actually wanted to build a computer, everything is there. Okay, so now I'm going to do the multiple list insertion, and this one is particularly interesting the way he's done it. I found a couple of things that were kind of tricky, kind of interesting. So let me switch to that. So this is the source. Let me paste the link to this. And so what's happening here? We discussed this when we read that section in TAOCP, but the basic idea is this, that in basic list insertion, he has one extra node at the beginning of the array that he calls the head node. And this head node is the start of the sorted list. So initially, when you start out, he initializes that head node to point to the very last record. Because we know that one record is always sorted, right? One key is always sorted. So he can easily do that initialization. And then we can go down the array and start comparing each of the unsorted keys and figure out what their place is in this sorted list. With multiple list insertion, the idea is that instead of having a single list, you have more than one list. And what you do is you map a range of your keys to each one of those lists. So first of all, that means you have to establish a range. And that's done by picking some power of 2. that will allow all of the keys to fit into that range. So one of the assumptions that's being made is that the keys this time are unsigned, so they're at least 0, so 0 or positive. In our previous step through, we saw that the test data had a negative value in there, so we won't be doing that in this step through. All of the keys will be at least 0. And I'm also using a bigger input data set here. It's the set of the 16 values that Knut has mentioned in the text, and he uses in various tables and examples. So that range, by the way, let me show you that data so you can see it. So this is the data. There are 16 values. If you look down here, this is the sorted, expected sorted sequence that we should end up with, or we should be able to figure out after the algorithm is done. So let me just go ahead and turn on some light here. Okay, so there are 16 values here, and they range from 61 to 908. So the range that's been picked for this particular data set is from 0 to 1023. So that's 2 to the power 10. And all of these keys fit into that range. So what this program will need is, first of all, what that exponent of 2 is that you're using. So in this case, that's 10. The second thing that this idea or this algorithm needs is how many lists do you want? How many partitions or buckets do you want this range from 0 to 1023 to be split into? And you can choose whatever you want, right? So there's performance analysis in TAOCP that tells you like what the expected performance will be for different number of buckets, but we're going to use 4. So the 4 buckets or the 4 lists would then correspond to, let's see, it's 1024, right? So for 1000, if you divide that by 4, you get 250. And so then there's 24 left over, so that would be 6 more. So that will be 256. So 0 to 255 will be the first bucket, and then 256 to 511 will be the second bucket, 512 to 7 something, whatever that power of 2 is. So you get the idea, right? So there's 4 buckets. And the way the lists are set up is that in the first program, we had just 1 list, so we just needed 1 extra node. Now that we have, we plan to use 4 lists, we'll just need 4 extra nodes. That's it. So these 4 extra nodes will act as heads of each of their list, but we are still going to pass through the original array. So there's very minimal extra space involved over here. And this time, because these lists, the head of these lists are separate from the original array, they actually don't need space for the keys even. All you need is space for the link. So the extra space is not, 4 times 2 octabytes, is exactly 4 octabytes. That's it. And that's where it actually gets a little tricky because he does it this way. Okay, so let us now start this program. All right, so when we start the program, let me get rid of some of these windows. Here we go. Okay, so here's the data. The data that we have actually down here. Yeah. So this is the data that I had oh, I'm sorry. I think that the data here is, oh, I'm looking at the wrong tab. I want to be looking at this tab here. Okay, somehow I must have switched the tabs. So the data here is these two lines, right? This is the unsorted data. So these are the 16 keys, and each record has two octas. The first octa is the link, just like before. The second octa is the key. And then there's still that artificial first record because 0 is still considered special. And so we don't want real data to be at index 0, even though the link is not going to be used in this first record. But we still have to keep it away from the real data because the only valid indexes for data or for the keys are greater than 0. Okay, so that's there. Then over here is where we have the heads of each of those lists. So since we have 4 lists that we plan to partition all of the keys into, M is 4. This is hard-coded somewhere. And so all we're doing over here is we're allocating space that starts at line 54 that is equivalent to this formula, 8 times M. So we're just adding that to the head's address, right? So all we're saying is move the location of the rest of the program and the directives to 8 times 4, 32 bytes past the point of heads. And so that's now reserving 4 octas for the heads. And each one of these octas will be the head of its own list. Okay, so that's there. And this is just the expected output. Again, for visual examination, we're not going to use that in the program. So when we start out, this is the main program. This main program is going to pass 1, 2, 3, 4 parameters to the sort subroutine. So the call to the sort subroutine is down here. And those 4 parameters are the address of the data array, the size of the data array, the address of the heads array, and the size of the heads array, right? The number of buckets or the number of lists. Okay, so, oh, I know why that happened, that switch. It's because I had not switched the program that the debugger needs to use to the multiple list. So you have to go in here in the sources dialog and you have to switch it. You have to enable this source file as the program to use in the debugger, and then you say okay, and then it's okay. So let me exit the other one and let's start with this one. Okay, so now we've started the right program. And actually, let me just go ahead. No, I'll leave that there. So let's see what we have at the beginning of this program. So this is the data in memory. There are 16 values in here, so I think I need to make this a little taller, maybe a bit more. Yeah, I think that's good. Okay, let me see what the last value was here. 765 and then 703. So if we look at memory down here, we can see that this is the data array. This is the first record, 503, second record, 87, third record, 512, and then this is the last one down here, 703. And then the other thing is that we want to look at the heads array. So the heads array, which has been allocated over here, and the way things work in MMIX is that you can use one of these global registers to keep the address of some data permanently there. So then you can always use that register, or at least I shouldn't say you, the assembler can always use that register throughout your program to calculate the right address when it needs it, when the program is running. And that means that we can use heads anywhere in the program because it has a greg just before it. This greg was the second greg that I have written, right? The first greg is up here. Every time you do a greg, you use the greg directive, it allocates a new global register, and it starts at 254. So that was the first one. And the one for heads is the second greg. So it's reserved register 253 for the address of heads. In this panel on the right hand side, this is showing all the used global registers. So you can see 254, which is the data array, has this address, and 253 has this address, which ends in 110, right? This is the data segment because it starts at 2. And so what I'm going to do is, in this second memory panel, I'll change this to show the heads array. So the heads array only has 4 octets. So let me make this a little smaller. So over here we have the 4 octets. This is the first octet, second octet, third octet, fourth octet. They're all 0 right now. So what's going to happen is that these heads are the heads of each of those lists, and when we start adding or figuring out the correct positions of each of those keys, the heads are going to change. These will be the beginnings of each one of those lists. So let's start stepping through, and what do we get here? We're just setting the various registers as parameters to pass to sort, and at this point we're going to enter the sort subroutine. So here we are. So once we're in the sort subroutine, the first thing it does is it clears the heads. The heads right now are all 0, but the subroutine is going to set them to 0 anyway. And so let's just step through that. That's the first loop. So in this loop over here, you'll see it go through these lines 4 times, and it's going to set each one of those entries to 0. We won't see any changes over here, so there's no highlighting because the values are already 0, so they're not going to change. So once the heads are all set to 0, this should be the last iteration. Yeah, there we go. So this is where it starts to get a little tricky. What's going to happen in this instruction is head right now is the address of the heads array. So head $2, meaning register 2, which is this one. You can see that this is some pretty big number, right? Because it's an address. It's this address down here of this array. Once this subtraction happens, it's going to subtract link, which is the address of the data array. So link is $0 here. This link is the address of this array, the data array. The heads array is after the data array. So the problem here is, or the reason why Knuth does this, is that these entries in the heads array, these are meant to be indexes into the data array. Okay, and he wants to use or access each individual head as if it were a link field in the data array. Now the link field is a field in one of the nodes in the data array, so it can be accessed through an offset from the base address of the data array, right? So if you wanted to access the link field of the third record and you know the start of the data array, you can just add 3 times the size of each node to the base address, and you would have the link field of that node. But now when we talk about the heads array, thanks Miguel, thanks for sticking around. So when we want to access the heads array, these are no longer records. These are just single octobytes. But to make the computation or the assembly pretty uniform, so there's no conditional checks like, are we at the start of the heads array or are we inside the data array itself, meaning looking at a link field in the data array? In order to avoid that, this is my understanding so far, why he's done it this way. What he's doing is he's turning the head register from an absolute address to an offset from the start of the data array. And you can do that by subtracting the address of the link, which is the start of the data array, from the address of the heads array, right? You subtract that, you get the offset between the heads array and the data array. And now that the head register will become an offset, what that means is that you can use that as if it were a link field in the data array. Okay, you can just use that offset because each one of these entries in the head array is meant to be used as a link field, even though it isn't strictly a link field in the data array. So this is a little confusing, I know, at the beginning, and it took me a little while to figure out like why he had done this, but it does make the code and the computation very compact. It avoids conditionals, it avoids branches for special cases, and it's actually quite interesting and cool, but you do need to figure this out in the beginning, like why is this being done this way? Okay, so we'll see that. After this instruction, you'll see that register 2 will turn from this big number into an offset, which is a small number. And let's do that. So that's the offset, 272. So 272 bytes is the offset between the start of the data array and the start of the heads array. And in the next instruction, we're setting up a base address register for the key fields. And this is done by adding the offset of a single key field to the base address of the data array, which is in the link register. and putting that into this register key, which is $4. So now this is the base address for the key fields. And so you can think of each one of these base address registers as serving a purpose of allowing you to skip over records in certain increments, right? So if you know that this field is at a certain offset in each record, then you just need to multiply that by some index and add that to the specific base address register for that field, and you will always have that field, right? So you don't need to go to the beginning of the record and then add an offset to that record to get to the field. You can just add the offset directly to the base address meant to be used just for that field. So that's how he does this and does this. And this is again a pattern that you'll see quite often in MMIX programs, especially the way they've been coded up for TAOCP. So that's there. And then over here in this instruction, we are initializing the J counter that we will be using to iterate over the data array to the size of the data array. And since this will be used as an offset, it needs to be scaled by the size of each record. The size of one record is 2 octets, which is 16 bytes. And the way that we're multiplying by 16 is by shifting left 4 bits. So that's what's happening here. And then once that's done, we jump into the first iteration of the nested loop. So down here. So I'm just going to pause for a minute, take a little break, and I will be back soon. Okay, we're back. So yeah, so got a little bit of replenishment. So what are we doing? We've got the first iteration. The first iteration over the array of unsorted keys. And what we're trying to do is to figure out which list is a particular key going to go into, right? We've got multiple lists this time. Each one of those lists has a head node over here. So we have allocated 4 head nodes. And these 4 head nodes correspond to a range of the keys, right? The complete range is from 0 to 2 to the 10. So from 0 to 1023. And when we look at one particular key, we will first compute which part of the range does this key belong to. We'll go to that head node and we'll start doing exactly what we did with the simple list insertion algorithm in the previous program. So let's do that. Let's step through this with step. And what's the first thing that's happening here? We are going to get the new unsorted key. So what's the first unsorted key? The first unsorted key is this one, the last key in the data array, 703. Now this is another big difference between this algorithm, which uses multiple lists, and the first simple list insertion. Because the simple list insertion had just one list, we could initialize that list head to be the very last key, because we know that, you know, it's already sorted, it's just one key, and we know that we don't need to find its proper position. Its proper position is just the first node in the list when it starts out. With these 4 partition lists, now we don't know like which key is going to go into which list. So all of these lists are going to start out empty. So that's a big difference as well in terms of the initialization. You can't, you have to deal with the empty list scenario. And I think that this is one of the exercises or one of the points that's made in TAOCP. But you'll see that is a slight difference as well. Because the very first thing that you'll have to do for each key is to figure out which list does it belong to. So first we get the key. So the first key we just said is going to be 703. So in register 8, which is the K register, we should see a 703. And that's what happened here. So we got the 703. The next step is to now figure out which list this key is associated with. So 703 should be, so there are 4 buckets or 4 lists, right? So the first one I said is going from 0 to 255. The second one goes from 256 to 511. And then the third one goes from 511 to 768, I guess. But whatever it is exactly, we know that 703 is going to be in this third bucket, right? So we expect this head to be the one that's going to be used, right? This is the third head. Now, I've explained the formula over here. Like, how does that association happen? And you can also hear the explanation that was given earlier in the Meetup discussion, right? But the way I've explained it here says there are M buckets, okay? And the range is from 0 to 2 to the E. E in this case is 10. So each bucket size, equal size buckets, each bucket size is 2 to the E. Remember, this is not the mathematical E, this is just some variable that we're calling E. And so in this case, it's 1024 is 2 to the 10th power, right? So 1024 divided by 4, that's the bucket size, or 256, right? So so that bucket size means that if you've got these values between 0 and 1023, and each one of them can belong to one of these buckets, you just need to divide by that bucket size to find out which bucket it belongs to. So, you know, you divide the key by 256, and, you know, it'll give you a multiple, which will be like 0 or 1 or, you know, 2 or 3 for values that are between 0 and 1024. And if you simplify this, right, you divide k by this expression, that turns out to be this expression, right? So you divide k by 2 to the E divided by m. That's the same as saying it's m times k divided by 2 to the E. And so that's another way of looking at this. So whichever, you know, whichever explanation you find easier, use that. You can explain this directly as well. So that will give you the index. This formula will give you the index of the bucket, or the index into the heads array. But remember that we want to work with offsets, not indexes, right? We have to work with bytes because these are offsets that we want to use with some base address. So to convert the index to a byte offset, we have to know what's the size of each entry, right? In this case, the heads array is an array of octabytes. So each one of these heads is 1 octabyte. So that means we have to scale the index by 8 bytes. We have to multiply it by 8 bytes. So instead of that separate multiply, what we're going to do is that when we divide by 2 to the E, we'll just build the multiplication into that, because we're not actually going to use a divide instruction. Because it's a power of 2 that we're dividing by, we can do a shift right. Right? When you want to divide by a power of 2, you can shift right. If you want to multiply by a power of 2, you do a shift left. So since we're dividing by 2 to the E, and we know that we will need to scale whatever that result is by 1 octabyte, which is 2 to the 3, we're going to divide by 2 to the E minus 3 instead. And if we're doing shifts, that means that we, instead of shifting E bits to the right, we'll shift E minus 3 bits to the right. So that's the entire formula for mapping a key to its bucket and coming up with the offset, not simply the index. So, okay, so that's what's going to happen in these next 2 instructions. We multiply by m to get, 703 times 4, which is 2812 over here. Then we do a shift right, and we get this 21. Okay, now what's interesting about this 21 is that this is the result of the division by 2 to the 10 and the multiplication by 2 to the 3. What's interesting is that this is supposed to be an offset into an array of octabytes. An octabyte is 8 bytes. If it's an offset into an array of octabytes, it better be, or we expect it to be, a multiple of 8. Because otherwise we're somewhere in the middle of the octa, right? So the first octa would be at an offset of 0. The second octa would be at an offset of 8. The third octa would be at an offset of 16. And then the fourth octa would be at an offset of 24. So the offsets, valid offsets, it seems, should be 0, 8, 16, and 24. But this is 21 here. So this is between 16 and 24. And it's not a multiple of 8. And at first, this looked like it was a problem to me. You know, like, is this computation right? What's going on? Why am I not getting a multiple of 8? And the reason why this is okay is because in MMIX, you can use any offset that you want. If you go back to the original discussion of, or the introduction to MMIX in Fascicle 1, and you remember the way memory is referenced, Knuth uses the notation M, capital M sub 2, capital M sub 4, capital M sub 8, right? And yeah, let me type that in here. M sub 2, M sub 4, M sub 8, right? And so then he would have, for example, something like M sub 8 of some address X, right? And maybe that address is M sub 8 of 1000. And what is this saying? This is saying, get me the octa, or I'm referencing the octabyte at address 1000. Let's say that that's hex 1000. So this is fine because you know, it's a multiple of 8. But what if it is M sub 8 of 1001 in hex, right? So that's not a multiple of 8. And is that valid? Yeah, it's valid because the way Knuth has set up MMIX and the way he defines this memory reference notation is that it refers to the octa that includes that address. And essentially what this means is that when doing memory references, the low bits of the address are ignored based on what sort of access you're doing. Are you doing an access to get an octabyte or a tetrabyte or a wide? And so if you're accessing something that's an octabyte, that's going to ignore the low 3 bits. And it will just, you know, get whatever the octabyte is corresponding to the resulting address. So 21 is fine as an offset into an array of octabytes, because what will happen is that the low 3 bits of 21 will be ignored and it'll end up being 16. So the octabyte starting at address 16 is the one that's going to be retrieved, and offset of 16 is fine. That just refers to the third octabyte, right? 0 is the offset of the first one, 8 is the offset of the second one, 16 is the offset of the third one. Okay, so that's what's going to happen here. We've done the mapping from the key to the list head that is associated with this key. And now we're just going to basically do what we did in the first program. We're going to figure out where this key should be inserted into this list. And to do that, we have to figure out what we're comparing it to. So this is, we're starting out with all of these heads empty. And so right now, there won't be any comparison. We'll just figure out that we're at the end of the sorted list. It's an empty sorted list. And we'll just insert, or we'll update the links so that they reflect that this is the first key in that sorted list. So what we expect is that the third head should get updated with the index or the offset to 703, which is the last node in the array. So let's see if that's what happens. Here's the update code, right? We are now at the end of the sorted list. That's this case. And in this case, we have to update those two links, right? We update the link of the previous, the trailing pointer Q to point to this new node, and then we need to update the link of the current unsorted key to point to the existing sorted key. In this case, it's null because the list is empty. So let's see if that's what happens. Yeah, so the third head down here got updated to 256, which should be the offset of this last key, 703. Okay, so let's see what else happens. Nothing else gets highlighted because the link for 703, which should point to the next sorted key that was already in the list, will remain 0 because the list was empty. So that's what happened. Nothing got highlighted. So now we go to the second iteration of the outer loop, and we are now going to look at the next unsorted key that's left. And so that's going to be 765. So at some point, we should be loading 765 over here as the key that we want to insert into one of these lists. Remember, the first thing again that needs to happen is figure out which bucket 765 belongs to. So looking at the value 765, we know that this will be mapped to the last bucket or the fourth head. So this is going to be the head that's going to be updated. So let's see if that happens. So we step through, we do the mapping, and then is that right? Is it the fourth one or the third one? I think it's the should be the fourth one, I thought. Let's see if that's what actually happens. We do the comparison, and no, it's being compared to 703. So 765. Oh yeah, 765 should be the third bucket because the fourth bucket starts at 768. So this is still the third bucket. So what we should expect to see here is in the third bucket, we've got a 256 as the first, as the offset into the first node, which we know is the offset of this key, 703. So when we compare 765 to 703, 765 will turn out to be bigger, which actually we've already done. right? So that was this one over here. That was the result of the comparison. And so we need to keep going in the sorted list. And since 703 is the last node currently in the sorted list, when we're now looking for the correct position for 765, it's going to end up at the end of the list. So let's see if that happens. So we are now going to update the links. We have found the correct position for 765, and this is at the end of the list. So what will happen? The current end of the list, which is this node for key 703, this needs to point to the new unsorted node, and its offset is 240, right? So this entry here is at offset 240. And the current head does not need to change because 703 is still the smallest entry. And the link of the new unsorted node needs to be set to 0. It's already 0, so it will be set, but we won't see it highlighted. So that's what will happen. And we go on to the next iteration of the loop. So for the third iteration, we're going to look at this key, 677, which is what happened here. And so 677 will again fall into the third bucket. So we're still in the same list, and it will first get compared to 703, and it will turn out to be less than 703, and so you get a -1. And that means that it needs to be inserted before 703. Since 703 right now is the first node in our list, in one of our lists, that means that the current unsorted node, which is this one, 677, will need to point to 703, and then the head of the third list will need to point to 677. So that should be the effect of the next few instructions at this point. So the first thing that happened was that the head got updated to point to the node for 677, and then 677 got updated, the link for 677 got updated to 256, which is the offset of 703. Okay, let's do maybe one or two more. So let me see. 612 will also be in the third bucket. Then 509, this should be in the second bucket. So we should see this second bucket get updated in the second iteration from now. So let's just do that quickly. First, let's see what happens with 612. So 612 will be inserted between 612 got inserted as the first node because it's smaller than 677, which was the previous first node. So now our third list is starting from here. You go here, which is 612. 612 takes you to 677. 677 then takes you to 703. 703 takes you to 765, which has the 0 link, which means it's the end of the list. So we have this list quite filled out, and let's now see what happens next. What is the next unsorted key to look at? That would be the one before 612, which is 509. So let's see where 509 gets picked up. At this point, 509 got picked up. We map 509 to one of the buckets, and it turns out to be bucket with offset 15. And so in terms of octabytes, this means this is the whole range from 8 to 15, right? So this is actually, think of it as offset 8, which is the second list. Okay, so let's step here. The second list is empty, so all that's going to happen is that there won't be any comparison. We'll reach the end of the list, and the head of the second list will be updated to the offset of 509, right, which is 192. Okay, this is just the same memory area that is overlapping over here. So that got highlighted because it's actually the same memory address. So, so now we've got the second list starting to fill out, and the first entry in that second list is 509. And the next entry, the next key to look at is 154. And 154 should fall into, or should get mapped to, the first list. So we should see an update to the first head down here. Okay, so let's see if that happens. Yep, that's what happened. The first head got updated to 176, which is the offset of this key that has the value 154. And yeah, so then we keep going. Let me now start setting some breakpoints so we can go through this a bit faster. Let me set a breakpoint at this branch, I think. So then we should be able to see the when a insertion takes place and the links get changed in the various lists. So let's do that. Continue. That was this key, 426. That got inserted into the second list. Okay, next, the key 653. Okay, so that got inserted into one of the lists. We can see the list that contains 612 is the one that got updated because 612 is now pointing to 653. And 653 is pointing to whatever 612 was pointing to before. All right, so the next key is 275. We should see its link possibly get updated unless it's the very last 275. It's not that small, so let's see. Yeah, so its link got updated to 160. It belongs to the second list, and so on. Okay, so this was the key 897, and then at some point the key 61, right? And now we're at this key 512. Now we're at key 87, and now we just have one unsorted key left, 503. In the next, at the next break, yeah, so that got updated. So now we have all of the keys with their links updated. They each belong to one of these four lists, right? One of these four lists down here. And I think that's about it. So yeah, so then you can see that we're now going to return from the subroutine, go back to the main program. So this is right after the call or the push J instruction in the main program. Down here. And I think that is it. Yeah, that's it as far as the program goes. We are done. As you can see, we still have the same original array with the keys exactly where they started out. The keys don't move. So this is a great algorithm and routine for sorting data in place by constructing the sorted sequence in another array, which is, part of the original array in the sense that it's just another field. So that each record has you can think of it as like a sort order link list field, right? So the link fields behave that way. They just tell you when you're at one particular record, what is the next record in sorted order. And in this case, we have multiple lists, but they're pretty easy to combine. You can just start at the first list being the list that's mapped to the first, range of the 4 buckets, and you follow that. You reach the end of that first list, then you go to the second list, and so on. So we essentially have the array sorted. I've added C programs for both of these algorithms, so you can look at those as well. Let me paste the URL for that. So if you go to this and so you can look at the C programs. They would be, I think, a little easier to understand, but they are they're pretty faithful to both the MMIX and the original algorithm, but they don't have any go-tos, and they don't play most of these tricks in terms of the offsets and the fields, because we're dealing with tight variables, and you can do that in C, but it gets a little ugly if you have to typecast things and access them in some unnatural way. But the steps, I think, map pretty easily to either MMIX or the algorithm. So depending on how what level of detail you want to understand, but certainly the implementation of all of these algorithms has a lot of details that you still have to figure out. So understanding the algorithm is one thing, but then understanding the code is another, or writing the code is another. So right now we do have the MMIX code available, although it's not in complete form as presented in TAOCP, and so that's one of the projects that we have is to make the MMIX code complete, testable, and then with more comments and easier to follow. So that's definitely one avenue that you can take in terms of understanding the algorithms. And it's nice because the algorithms do map quite well to the MMIX programs, just because in the algorithms, Knuth does use gotos, right? So at some level, you do have to understand the gotos. And at that level, possibly MMIX is a good choice because it will be pretty close to the algorithm. When you look at my C program or anyone else's attempt to implement one of these algorithms in a higher level language, we will try to use other higher level constructs, and then that's where there is going to be some difference between how people understand the algorithm and what their preferences are, what their style is, and that may be also like difficult to reconcile if you're reading the algorithm and you look at a program. Is this absolutely correct? Are they doing exactly what's been done in the algorithm? Some of these things can be tricky in the algorithm. So you can, if you stray too much in your implementation, you could make those mistakes. So that's one of the reasons why I feel like MMIX is really good, because it does map quite well to the algorithms in the book. Whereas any other language, there would be some differences that can be problematic if you're not careful. And I've certainly felt that when I was writing the C code for these algorithms, where I had to decide, like, how faithful do I want to be to the original algorithm? And I've tried to lean towards being more faithful, as reasonably faithful as possible within C. C is still not that high level, just in terms of dealing with memory, in terms of dealing with iteration and list. C is pretty close to what you can do in assembly and in the algorithms, but I don't use gotos. So gotos are strictly forbidden in my C programs. I've got loops, but I do try to match up the loops in a natural way, so that even though I'm not using gotos, you can still kind of see where each step corresponds to in a more structured flow. Okay, so that does it for today. Let's see, let me switch to the slides. So these are our resources. Everything is on GitHub and YouTube. And if you want to continue some topic, discussing it, there's the Facebook group. We also have an IRC channel, which is on the Meetup page. I should put the Meetup link here as well, and the IRC link here as well. But it's #TAOCP. So let me just type that in here. And I think that is about it. So yeah, so these are the two programs that we stepped through. Program L, list insertion, and program N, multiple list insertion. So thank you very much for sticking around till the end. And thanks again to all our members who attended today, Michael and Arthur and Miguel, and everyone who's watching. And if you have a chance to comment and provide feedback, please add comments to the YouTube video. And best of all, if you can join us in the meetup, that would be great. But thanks again. Bye-bye.